Welcome to this short video looking at the dataset we've created for our ICASSP 2026 Signal Processing Grand Challenge. We're trying to predict lyric intelligibility. This is part of the Cadenza project. My name is Trevor Cox. The website at cadenzachallenege.org has full rules, baseline, how you register, how you download the data, and a lot more detail than I'm going to go into in this video. So I'm just going to give a brief overview of the data and give you a sense of some of the challenges you might face working with it and hopefully inspire you to tackle some of the research challenges. So there is another video which gives you an overview of the challenge. I'm just going to give you a very simplified view of it, enough for you to just kind of get a sense of the data. So imagine someone is in the room and they're listening to a short snippet of music. That's audio one. They've been told to write down the lyrics they heard. And from that, we calculate their speech intelligibility, which is the fraction of words in the lyrics they correctly identified. That's the target. So your task in this challenge is to predict the target, the speech intelligibility, from the audio. So we had to create a brand new data set for this. If you want to know more about the data set generation, it's on our website. But it's basically Western popular music, a lot of different genres from the FMA database. But there's a lot of processing to get things like select the tracks, get the ground truth, and also get the lyric intelligibility through our set of listening tests. So here we have on the left-hand side, we have count. So this is just a frequency distribution versus intelligibility. So that's the scores people got in the listening tests. And I guess the first thing you spot when you look at this is there's quite a lot of people who either got intelligibility of 0, meaning they got no words right when they were asked to write them down, or intelligibility of 1, meaning they got all the words correct. And this might look, initially, oh, this is a slightly odd distribution, but this is really what people did listening to genuine pieces of music. So we didn't want to try and manipulate it to get more data in the middle, because this reflects how people behave when asked to do this task. So it's an interesting distribution to work with, distributed between 0 and 1, but there's obviously quite a lot at both ends. Now, if we start looking at some of the challenges that you'll have in modeling the data, the first one, which I haven't mentioned in this video, is there's hearing loss simulation going on. So some of the audio tracks were just as they came off the FMA database. So they were just the original piece of music. Take this one, for example. Truly alone, I am truly alone. But some of the tracks had hearing loss simulation on them, which changes, it attenuates the high frequencies and sometimes adds distortion. So as you can imagine, simulating hearing loss degrades your ability to pick out the lyrics. And it's just like if you've dealt with speech intelligibility, it's just a degradation of the signal with some noise and distortion and change in EQ, a kind of thing that you're probably used to dealing with if you do speech intelligibility work. So when we look at, I'll go back to my data here. I've now split it with our different kind of hearing loss levels. So green is no hearing loss, orange is a mild simulated hearing loss, and blue is a moderate simulated hearing loss for the track. And you can see if we look at these intelligibility equals 0 cases, probably not a big surprise that as we add hearing loss simulation, they get less intelligible. And a lot of this stuff at the 0 is actually dominated by the hearing loss simulation. And if we look at the high end, we can see that the ones without loss are the ones which tend to score 100% or 1 in the fractional intelligibility. So maybe not that surprising, but that's one of the things you have to model is maybe the effects of hearing loss. And we give you in the metadata whether there's no loss, mild loss, and moderate loss of the data you're working on. Now, you don't really need to understand what the hearing loss simulation is doing. You can just treat that as distorted music. But if you want to know more about it, it's available on the PyClarity GitHub, and you can take it apart and find out more about how this Cambridge hearing loss simulation works. So what about another challenge? Well, I suppose it's obvious that you might get energetic masking. So you've got other instruments accompanying the singer. You know, if this was a rock band, you'd have drums and bass and guitars and other things going on. But sometimes there's also noise that might surprise you if you don't listen through. There's some historic recordings that actually have noise added. They are phonographs, so you can hear the scratching of the noise on the track. So potentially these accompaniments can mask the speech and obviously degrade intelligibility. Here's an example actually of one of those phonograph recordings.
You remember Nathan, who treated me so rotten. Satan, so played it be so rotten.
So you'll notice I've played it twice. And the reason I played it twice is that is what the people in the listening test heard. So they heard it twice because it takes you a little bit of time to get your ear into the music, and then you can hear it again so you can get the lyrics correctly. So one of the reasons we have quite a few zero intelligibilities is we didn't let people just listen on and on and on and again, trying to get every word correct. This was kind of listen twice, give us the lyrics. So what other challenges might you meet in the data set? Well, one thing which you wouldn't normally meet on speech is there's sound engineerings on the vocal. So something audio engineering does, if you record a vocal in a studio, that's very rarely used as is. You would have double tracking where you have multiple versions of the same vocal on top of each other, or maybe different sung versions on top of each other. You might have backing singers harmonizing odd words or odd phrases. You'll have chorus added, reverb added. You'll have compression almost certainly. You might have some EQ. And of course, you've got things like auto tune might be applied to if your singer was going out of tune, or even for effects. And you might get things like de-essing to get rid of sibilant effects. So there's a whole lot of things that might be on the vocals. And if you're used to dealing with speech intelligibility, these aren't things that you're probably used to having on the clean vocal signal. Let me give you an example here. Here's an extract which it's got really clear lyrics to them. Here's the actual track.
You're not as good as you think you are. You're not as good as you think you are.
You're not as good as you think you are. I think that's fairly clear. Now listen to the vocals. These have been extracted using musical source separation, but listen to the quality of them and you'll notice they've got quite a lot of effects added to them.
You're not as good as you think you are.
So you can hear some echo on that, and there's actually some double tracking, I think, as well. So if you try and do musical source separation to get to the vocals, you can expect to have some audio engineering effects on top as well. And those can also affect intelligibility, depending on how severe the effect has been added, and that comes down to artistic decisions by the sound engineers. So let's look at a fourth case, which comes down to people not singing very clearly. And a lot of tests you do on speech intelligibility are done where people have been asked to speak very clearly, and therefore, the words are very clear before they get degraded. Well, that's not the case in singing. Quite often, words are garbled because they have to fit in with a song in terms of the melody or the rhythm. And sometimes it's just a stylistic choice. We can probably all name singers who don't sing very intelligibly. And if you go on the internet, you can find lots of examples where people have had fun sort of mishearing lyrics and saying all the things they kind of misheard rather than the real words. Here's an example of some unclear singing where the vocals are perfectly prominent, but getting the words is really difficult.
I'll even let you sneak a I'll even let you sneak a
I mean, maybe sneakers is in there. I mean, that's really difficult. And I've heard that a lot of times to actually get the correct words out of that particular phrase. So you can expect the sort of vocals that start off, even before it's mixed in with other instruments, to sometimes not be very clear. I haven't looked at the literature, but I suspect there's more redundancy and it's easier to guess the lyrics in many cases because of the fact that there's some sort of phrases, some cliches that often get used. But certainly, if you were setting a language model up to deal with singing, it would be a different language model than dealing with spoken language. So here's one which has got a really common phrase played in it. So it's quite hard to hear a lot of those words, but I Want To was really clear. And so I'm not sure I've got the best example there. I need to hunt the database for a better one. But phrases really do reappear very frequently. I should point out, by the way, in these samples, there's an odd one I've heard, but it's meant to be unfamiliar songs. So nearly all of them, the people wouldn't have known what the phrases are meant to be. So they're really working from kind of fresh when they heard them for the first time. So that was my kind of list of things you might find interesting in the data. Maybe there's other stuff, and feel free to sort of kind of get in touch if you think I've missed a factor which is important. And go to our website, cadenzachallenege.org, Download the data and you can have a play with it yourself. But if you've got any further questions or any help you need with this challenge, please just get in touch.